All right. Hey, everybody. So in this video, we are going to introduce a test to see whether or not a given series converges. This will become a common theme of ours going forward. We are going to try to collect more and more and more tests to see whether or not a given series will converge or diverge, right? This is important because, as we've seen, just because the terms of a series go to zero does not necessarily mean that the series itself converges. So we'll have to develop more robust tests to help us figure this out. So we're going to introduce this new test, something called the integral test. We're going to define the integral test, explain the idea behind it, see why it works, and then we're going to use it to prove, once again, that the harmonic series actually diverges. So let's talk about, let's move this video. Let's talk about the idea behind the integral test. So we are going to start with, or I should say the integral test will be used for sequences that are positive and decreasing, meaning that the individual terms in the series, I should say, this will be used for series whose individual terms could be thought of as a sequence that is positive and decreasing. So let's suppose that we have a series, or a sequence rather. So if these are the numbers 1, 2, 3, 4, 5, and so on. Let's say that our sequence elements, we have this is a sub 1, this is a sub 2, a sub 3, a sub 4, a sub 5, and so on. I'm going to draw in the rest of these, but you can see as I'm doing this that these individual terms, these individual numbers are positive, they're above the x-axis, but they are all decreasing, right? So they're getting closer and closer to zero. And then we might ask about the, question, so if our first term is A1 and then A2, A3, et cetera, what can we say about the series? Right, what can we say about the series A1 plus A2 plus A3 plus ... Right, so what can we say about that infinite series? So here is the idea behind the integral test. We're going to identify this sequence with a function f for which a sub n is equal to f of n, and f of x is going to be positive, decreasing, continuous function. So the idea is we're going to identify an appropriate function f of x, and it just so happens that f at our integers, f of n, is equal to a sub n. So f of x, which I'm going to draw here, and which I'm going to draw, I think, in orange, right? F of x is going to be a function that is positive, that is decreasing, that is continuous, and that happens to go through all of these points in our sequence. And we'll just continue that on down there. So that's in orange, our function f of x. Now, why might we consider a function f of x? Well, if I want to consider an appropriate improper integral, let's say the integral from 1 to infinity of f of x dx, right? Well, that integral will be all of the area from 1 to infinity under this curve, right? So let me really poorly sketch that in here. That's going to be all of this area down here, right? All of that area. And so we can compare that to our actual series, a sub 1 plus a sub 2 plus a sub 3 plus ... And to do that, let me switch back to purple. Notice that a sub 1, right? So a sub 1 is our first number that we enter. Well, this was at height a sub 1. And so a sub 1 can be realized visually as the area of this rectangle here, right? Because this rectangle has height a sub 1 and has width 1. And so a sub 1 is really that width right there. I'm sorry, a sub 1 is really that area right there. Similarly, a sub 2 would be represented visually as the area of this rectangle. with height a sub 2 and width 1. A sub 3 would be the area of this rectangle. A sub 4 would be the area of this rectangle, and so on and so on. And so what we see then is actually that we can directly compare the definite integral that we were computing, that's the area in orange, with the infinite series, that's this area of all of these rectangles. And we see that the area of all of these rectangles added together, it's actually going to be to use our language from Riemann sums, this would be like a Riemann sum that is an overestimate for the area. In other words, the area of all these rectangles is going to be bigger than the area that is just under the curve, right? We see all of these extra little pieces here, right? So this piece here, that piece there, and so on. All of those extra pieces, are going to be, overestimating the area of the integral. And so what we're going to see then is, let me switch to colors here, that if I were to measure this improper infinite integral and compare it to this series, we would see that the area formed by the series is actually bigger than or equal to, really it's going to be bigger than the infinite integral, the improper integral. And so that gives us a direct way to compare these two. And specifically, if our improper integral doesn't converge, if our improper integral goes to infinity, that will mean that our series does as well. In other words, if the orange area is actually infinite, then the purple area, the area of those rectangles, will also necessarily be infinite. And the end result that we get there is going to be that if that improper integral diverges, then the corresponding area will also diverge. Now, it turns out that we can say a similar statement about converses. And to do that, let me draw what's basically the same picture, but let me draw it over on this other screen here. Okay, so hopefully we just cut to a scene where now I have this picture drawn on the right. So I'm going to draw basically the same picture, except when I draw my rectangles, so maybe I should say this, so my area will still be the same, my integral from 1 to infinity of f of x dx, right? That'll still be the same. We're starting here at 1. So it's going to be all of this sort of shaded area here, right, going off to infinity. So we have the similar picture. Now, when I go to draw my series, though, instead of drawing all of my rectangles like I did before, where I went sort of up at the point and then over to the right, let me go and start at my rectangles, drawing them at the point and over to the left. And I'm actually going to start here at my second element, right? So I'm going to start with a sub 2 and go over and down, right? So that's a sub 2. Next, I could do a sub 3. Okay, so that's up and over and then down. That's going to be a sub 3. And then I'm going to go for a sub 4. That's up and over and down. That's plus a sub 4. And I can continue this. So there's my dot, dot, dot. And notice, if I'm going up and over to the left, what I'm actually getting is an underestimate. These rectangles fall under the curve. And so as a result, if I went to try to compare the improper integral from 1 to infinity of f of x dx, and I went to compare this series, notice I'm leaving off that first term, right? So a sub 1 is not appearing, but I still have a sub 2, a sub 3, et cetera, and I have all infinitely many of those. So if I'm comparing the series minus the first term to the improper integral, in this case, I'm getting that the improper integral is actually bigger than or equal to the term or the series minus the first term. And so that is fantastic, because if our improper integral converges, right? So if that area is finite, then so is the series minus the first term. And if the series minus the first term is finite, then the entire series will also be finite. Adding in that first term, throwing it back in, we'll lose this inequality, but if this was originally finite, then the full series is going to be finite as well. What this does, what these two pictures do, is they allow us to directly compare improper integrals to series. Maybe I should say that in the other direction. It allows us to compare series to improper integrals and allow us to draw conclusions about convergence versus divergence of those series based on the convergence and divergence of the integrals. And so what we get then, so what we've seen allows us to come up with this new thing which we'll call the integral test, right? As before, we're going to take a series whose individual terms form a sequence a sub n, and let's identify this sequence a sub n with a function f of x that is positive, decreasing, and continuous for all x bigger than or equal to 1. What we can do then is we can compare the infinite series to the improper integral from 1 to infinity, and we see that they align on matters of convergence and divergence. So if our improper integral converges, which we can compute just using our knowledge of improper integration, then the corresponding series will also converge. Similarly, if our improper integral diverges, then our infinite series will also diverge. And that is our integral test. Now, to see this in action, recall our harmonic series, which is our favorite new series that we've seen. That was of the form, so if this is height 1, then that would be 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, and so on, dot, 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 right? And what we can do then is we can compare the harmonic series with the function f of x equals 1 over x, which I will sketch in here. So this is our function, f of x equals 1 over x. Right? This function is continuous, this function is decreasing, this function is positive. And so what I can do is I can directly compare the harmonic series to the integral from 1 to infinity of f of x dx. Right? And as a reminder, we compute that because it's improper. We take a limit as b goes to infinity of the integral from 1 to b of, and now this is 1 over x dx. That's going to be the limit as b goes to infinity. The antiderivative of 1 over x is just ln of x, evaluated from 1 to b. And so that's going to equal the limit as b goes to infinity of ln of b minus ln of 1. ln of 1, of course, is just 0, so that disappears. But as b goes to infinity, ln of b also goes to infinity, right? The ln function grows very, very, very slowly, but it does keep growing, and it does diverge to infinity, right? And so we could say that this diverges to infinity. And because it diverges to infinity, albeit very, very slowly, that means that our harmonic series, though it will grow very, very, very slowly, will also continue to grow and eventually grow to infinity.